Imagine a straight needle resting on a blank sheet of paper. What is the absolute smallest piece of paper you'd need to rotate that needle a full 360 degrees without it slipping off the edge? Most of us instinctively picture a perfect circle with a diameter matching the exact length of the needle. We assume the needle requires a container at least as large as itself to sweep around. For centuries, this felt like an unshakable fact of geometry. No one saw a reason to question the idea that rotation requires a specific minimum amount of open space. That changed in 1917, when Sōichi Kakeya proposed the problem and mathematicians began to realize the required area could be squeezed much tighter than anyone expected. This simple geometry puzzle eventually revealed a massive flaw in how we perceive the relationship between an object and the space it occupies. The first breakthrough came from trading the circle for a deltoid. By using these sharp corners, the needle still completes a full rotation in a visibly smaller footprint. Mathematicians then slice these shapes into thin segments, sliding them to overlap at the center. In this overlapping design, the needle must scrape through tight corridors, shifting its angle slightly at each intersection. Every time the segments are made thinner and overlapped more aggressively, the total area on the paper keeps dropping. The physical needle remains a constant length, yet the space it needs to complete its rotation is rapidly disappearing. Mathematicians realized that if they repeated this process of splitting and shifting indefinitely, a concept known as a limit, the total area could shrink toward zero. It never hits absolute zero, but it can get as close as you want while still allowing the needle to turn. Every proof respects two strict rules. The needle never leaves the shape's boundary, and overlapping sections are only counted once toward the final area. The construction works by folding the required space into an increasingly complicated tree-like network of extremely thin directions. The needle slides down one microscopic branch, adjusts its angle, and slides up the next. This shows that a rotating object doesn't need a wide open void. It only needs access to a specific, precise collection of angles. A region that appears mathematically empty can still provide enough structural support to house a moving physical object, provided the boundary geometry is complex enough. To understand why a shape with near-zero area behaves this way, we have to look at its fractal dimension, a measurement of how much detail is packed into a space. While the traditional 2D area on the left shrinks toward nothing, the underlying structural complexity on the right remains high. This object occupies more mathematical structure than our eyes are capable of detecting on a flat sheet of paper. Regions that look like empty space are actually packed with infinitely intricate, repeating geometry. We judge the capacity of a space by its visible surface area, often overlooking the structural density that can exist within it. These Kakeya sets eventually appeared in completely different branches of mathematics, far beyond simple geometry. They are central to harmonic analysis, to wave propagation, and partial differential equations. They impact signal processing and digital data compression. Calculating how these sets behave in higher dimensions, the Kakeya Conjecture, remains one of the most significant unsolved problems in analysis. Some of the world's most accomplished mathematicians, including Terence Tao, are currently working to find a solution. A single rotating needle challenges how we define a container, proving that a shape with nearly zero area can still hold the infinitely many directions a needle needs to turn.